record this, right?
Absolutely.
Okay, good. So it's my pleasure today to introduce Carla Verdi. Carla did her bachelor's and master's degrees both at the University of Padua and Padua. I'm not quite sure how you pronounce.
Padua is the Italian name.
And then she did her PhD at Oxford with Feliciano Giustino, and now presently is a post. I guess I was in. Oh, I forgot to write down the dates. 2017, but maybe we shouldn't say dates anyway. And now she's a postdoc at the University of Vienna. I believe you're working in the group of Georg Kresse.
Yes.
So that's the people who develop and maintain the VASP codes for people who like electronic calculations. So our scientific paths have crossed a few times. I mean, we've been interested in similar problems about electron-phonon coupling in recent years, and Carla has done really important work on implementing the full calculations of the Fröhlich coupling in electron-phonon coupling in ionic materials, and push that further to how we can calculate polarons fully from first principles these days. And that's what she's going to tell us about today. So with that, take it away.
Brilliant. Thank you for the introduction. So I will start sharing my screen. Perfect. So let me just make it full screen. Okay, I hope you see my presentation.
Yes, yes.
So thank you very much for the invitation to speak, even if virtually, and to be with you today. So I also wanted to say a couple of words about what I do and where I am. So I just start with this very pretty picture of Oxford, where I did my PhD and also a short postdoc afterwards. So it's very small, but absolutely stunning. And I can say that I moved from the city of the dreaming spires, this is how people call it, to the city of dreams, thanks to this guy here. And it's again another beautiful city, Vienna. And as Walter was saying before, it's also the city where the code VASP is developed. So this is one of the most used, or even the most used first principles code in the world. So the VASP development team is there, and I now work with Georg Kresse, who is the head of the VASP, which is now actually a software company. Before, I was in the materials modeling and design group in Oxford, and I was actually working with another very big first principles code, which is Quantum Espresso. So as Walter was saying, I will talk mainly about first principles calculations of polarons. This is not actually what I work on at the moment, but it's actually work that I've done mainly while in Oxford during a few years. And of course, it's not work that I've done by myself, but I will have the chance to acknowledge everyone during my talk. So first of all, I should also say a couple of words about what polarons are and why we should be interested in studying them. So I will just use the help of this nice sketch that I took from a very recent Nature Materials publication that dealt with polarons in hybrid lead iodide perovskites. So just to let you understand that, well, people are very interested in this sort of quasi-particle, and they play a major role in materials that have important applications, such as these halide perovskites. So what happens is that when you take ideally a crystal, an insulator or a semiconductor, and you put an electron in there, so you add an electron, this electron is not necessarily free. It moves around in the crystal, and it can induce a distortion in the lattice. So the atoms that form the crystal lattice can actually move as well. And then what can happen is that the electron gets trapped by this polarization field that it induced itself. So this is why it's called Polaron Self-Trapping. And this can happen in particular in ionic materials, but not necessarily. And since we're physicists, we like calling things differently. We like using quasiparticles. So this quasiparticle has been named Polaron. And so it's formed by the electron and this kind of phonon cloud around itself. So phonons are, of course, the quasiparticles that describe the lattice vibrations. Now, the properties of the crystal can be really affected by the presence of polarons. For example, there can be distortions in the crystal lattice, and the electronic properties can change dramatically. For example, the effective mass of the electrons can increase substantially. And in general, there can be more or less a large degree of localization of the electronic wave function, depending on how strong the interaction with these phonons is. Now, I will briefly sketch the outline of the talk. So the talk will be kind of divided into two parts. So the first part will deal with polarons as observed in ARPES spectra, so angle-resolved photoemission spectroscopy, and I will explain why we are particularly interested in this ARPES experiments. And the first material I will talk about is anatase TiO2, and I call this part theory meets experiment because it's kind of it's where everything started, how we started doing calculations on this sort of properties. And this was done with Feliciano Giustino and also Fabio Caruso in Oxford. We also worked a lot on another material, which is European oxide. And I call this experiment meets theory because in this case, it was Professor Phil King from the University of St. Andrews in the UK and his student Jonathan, who contacted us, showing us some really nice ARPES results on this material. And then we did some calculations that added some more to what we already knew about TiO2. And in the second part of the talk, instead, I will talk more specifically about Polaron self-trapping and how we can construct an ab initio theory to describe this polaronic self-trapping that I talked about before, and also then calculate the wave function and the energetics of this polaron. And this was done mainly by, the theory was worked out mainly by Wenggong Xiu, also at the University of Oxford. And Samuel Ponce helped us a lot with the actual implementation of the theory. Now, I apologize if there's some experts in the audience who know already everything about ARPES and spectroscopy experiments, but I'll just say very few words. So in an angle-resolved photoemission spectroscopy experiment, what people do is essentially shine light on a sample and then probe the electrons that get emitted by the sample. And basically by measuring the energies and momenta of the electrons, one can really map the band structure of a material. This is of course well known and very old, but the progress that has been made by experimentalists in this field in the last 10, 20 years is really, really impressive. So for example, this is the band structure of some transition metal like chalcogenide. And you see here, it's particularly shown the region of energies near the band gap. But what is really impressive is that nowadays experimentalists can reach a level of resolution that was really unimaginable years ago. And so what people can do is to really probe the many-body physics in the materials. So you can probe all sorts of many-body interactions. So of course, electron correlations, but also the interaction of electrons with phonons. Now remember, phonons have energies of the order of 50 milliV or 100 up to 100 milliV or so in this sort of solid state materials. So you really need a very low energy resolution in order to resolve structures that are related to the coupling with phonons. In fact, there was a very nice experiment that was published back in 2013 by the group of Marco Grioni at EPFL. And they measured, they did ARPES on anatase TiO2. So to do ARPES, you dope the material. So there will be a pocket of electrons near the bottom of the conduction band shown here. This is the gamma point, the center of the Brillouin zone. When you look at the ARPES intensity map, you see something quite different to what you would normally expect to see. So there is a parabolic band here. Of course, there is a lot of broadening, but again, we're looking at energy scales of just a few hundred milli-electron volts. So there is a parabolic band, and this is followed by another parabolic band and some more tail. And if you look at the energy distribution curve, so you cut this at the center, k equals 0, you see actually a series of peaks. So there is the first main peak and then satellites. Actually, maybe I haven't used the word satellites yet. This is how people call this. And if you go into textbooks, you can see that this sort of feature can be attributed to the coupling of electrons to longitudinal optical phonons. Why? Because in particular, you can see that these peaks are equally spaced, and the spacing of the peak is actually of the order of magnitude of the main longitudinal optical phonon energy. And there is more. There's the fact that if you measure the spectra at different doping levels, at different carrier concentration, you will see that the ARPES map has an interesting evolution with the doping. So you go from a low doping behavior where you have quite clearly the main band and the satellite and the tail, then similar at intermediate doping, and then at high doping, you have basically something that is more like a kink in the band structure. There are other very famous examples. For example, this was published in Nature, and it deals with monolayer iron selenide on strontium titanate. And this is a hole band, and this is an electron band. It's not very clear from the ARPES intensive map itself, but when you look at the second derivative plot, you can see more clearly that there is a band and the satellite can be resolved apparently also for the whole band, although you can see it less clearly. And this is another famous example published in Nature Materials, and it's the 2D electron gas at the surface of strontium titanate. You see the band here, followed by a satellite. There is this cascade, but it's kind of due to background signal. And again, the second derivative plot really helps us in discerning the real spectral features. And you see that, again, there are these satellites that are spaced at multiples of the phonon energy. And again, we can observe the evolution of this behavior with doping, and we see that again, at highest doping, we have more like a kink and a very broad tail rather than the satellite features. So now the real challenge is, can we calculate this from first principles? Can we actually confirm that this is the many-body physics that is going on? And even more, can we understand and predict the behavior with increasing doping? The answer is yes, we can, although it's not that easy. And I will show you what we did. Of course, more can be done as well. So first of all, let me start by explaining that in terms of many-body perturbation theory, when we look at the ARPES photocurrent, we can actually say that this measures the electron spectral function. This is within the so-called sudden approximation, so neglecting photon cross-section effects or neglecting the fact that the electron could interact more with the material before being emitted and so on. But basically, if this is the ARPES photocurrent, then we have the electron spectral function, which is called A, And the electron spectral function is proportional to the imaginary part of the Green's function. Now, if we just take a very, very simple representation of what happens to our electrons in the material, if we have a theory where the electrons are non-interacting, the spectral function will basically be a delta function peak. And then when many body interactions are switched on, then what happens is that this quasi-particle, the particle peak can shift, it broadens, and there can also be these additional features that we call satellite appearing. The many body effects are included by a so-called electron self-energy. And this is what we are interested in calculating, basically. The electron-phonon self-energy, the dynamical electron-phonon self-energy, is given by this expression here. I will briefly walk you through what this all means. So we have N is the electron index, K is the electron momentum. We have a summation over bands, summation over phonomodes and phonomomenta. G is the electron-phonon matrix element. N is the Bose-Einstein occupation factor. F is the Fermi-Dirac one. And then we have the electron energies and the phonon energies. So as I was saying, G is the matrix element. This is the trickiest part in this expression. It basically is given by the probability amplitude of an electron that is in an initial state Nk to be scattered in a state Mk plus Q by a phonon perturbation. There is an additional caveat, which is the fact that it is important to include in these calculations non-adiabatic effects. What does this mean? When we dope the material, there are these additional electrons in the conduction band bottom, and these electrons can further screen the electron-phonon interactions. And this needs to be taken into account in a dynamical way by further screening the electron-phonon matrix elements by the electron dielectric function, which is, in this case, it can actually be approximated by the dielectric function of an electron gas, because we're just describing the electron gas at the bottom of the conduction band. Now, this whole self-energy, to calculate it is actually quite expensive. In particular, the electron-phonon matrix elements, they can be obtained by what is called density functional perturbation theory, but it is expensive. And what you need to be careful about is that these summations over bands and Brillouin zone momenta, they require up to a million of points. And this is because of the very small energy scales involved and the rapidly fluctuating functions. So in these calculations are performed using this code called EPW, which is part of the quantum espresso distribution. And all the details are included in these references. But basically, what EPW does is that it implements a clever strategy called Varnier-Fourier interpolation in order to interpolate these matrix elements and also the band structure and the phonon band structure onto very fine grids in the Brillouin zone with the cost of calculations simply performed on very coarse grids. So this is very important to make these calculations feasible. Now let's move on to the spectral function. In many-body perturbation theory, within the so-called Dyson equation, the spectral function is calculated from, as I said, the imaginary part of the Green's function. And it's this expression here called the Migdal approximation, which is basically what is called the Dyson equation. There is a better approximation that one can do, and it's called the Cumulant Expansion. I don't need to go into many details, but basically it means that you're including some additional diagrams that are not included in the first expression here in the Migdal approximation. So it is more accurate, and it still requires only the calculation of the self-energy that I showed you before. And this technique has been used in many papers in the past, but mainly it concerned the description of electronic correlations. So when you want to calculate electronic correlations, you would do generally GW calculations. And if you look at the spectral functions, you can also see some satellites there. Of course, we're talking about energy scales that are an order of magnitude larger than the ones that we're looking at now. But still, you see these satellite features in the experiments. And if you do a standard GW calculation, the satellite occurs at kind of like the wrong energy. But then when you use this cumulant expansion method, the satellite is captured at the correct energy. And it's us and some other groups that recently started using this method also for electron-phonon coupling calculations. So let's move on to some results. So we did the calculations on anatase TiO2 as anticipated. This is the bottom of the conduction band of the material, okay? So it is anisotropic. And this is just a sketch of a representative calculation of a spectral function where you see the main peak near the Fermi level and the cascade of satellites. If you track the maxima of these bands, then you can actually get these lines here. So the red line is the unrenormalized band. So what you would get by a standard density functional theory calculation. And then in blue, we have the renormalized band and the satellites as well. And we can actually see from our calculations that these satellites really arise from the interaction of electrons with this longitudinal optical phonons. So there is one which corresponds to an in-plane vibration and another one that is an out-of-plane vibration of the atoms. Let me dive a little bit more in detail. So this is a comparison of the ARPES experiments that I showed you before and our own calculations. So you can see that we essentially capture what is observed. So at low and intermediate doping, we have these satellites, and at larger doping, we mainly have a kink and broadening of the band structure. We can do a bit more. We can actually examine the many-body effects in these calculations. So what is really going on? In particular, remember in the self-energy that I showed you before, you had to sum over all different phonon modes. So if you artificially exclude some of these phonons from the calculation, then you can really identify which are the main contributions to the polaronic satellites. So here you can see on the left, it's a calculation with all modes included. By the way, you can see that the features, the spectral features are a little bit sharper than in the plot before. This is because before we included some more broadening to compare with the experiment, because in the experiment there are larger broadening effects. Then if we exclude the longitudinal optical EU mode, we get this plot on the right. So you can see that the main band is less renormalized and the satellite is more dim, and the second satellite, well, it's very dim, but on the right, you really can't see it anymore. So you can actually say that this polaronic state is mainly due to the interaction with this longitudinal optical mode. Yes?
Okay. No, with that.
So another thing, another interesting comparison is the comparison between the spectral function that you calculate from the cumulant expansion and from the Migdal approximation. So it's similar to what I showed you before in an angle in an integrated spectrum. So here you see that with the Migdal approximation, the satellite occurs at a much lower energy, and also you can only ever capture one satellite within the Migdal approximation. Finally, the effect of screening on the electron-phonon coupling. So this is the case of larger doping. And you see on the right, what happens if you don't screen the matrix element. So if you don't include the screening from the electron gas at the bottom of the conduction band, you see that there is this huge renormalization, which is not what is observed in the experiments. To be more quantitative, one can actually estimate the mass renormalization. So our electronic polaron has a certain, well, the electron has a certain effective mass, which is we call it here the bare effective mass from what you get from, let's say, a DFT calculation. And due to the electron-phonon coupling, it will have a larger mass, which is called here m star. And the mass renormalization parameter is actually estimated from the self-energy again. So this is plotted in blue here, the lambda parameter. So you see that the renormalization is roughly constant at low and intermediate doping level, and then it drops. So it becomes much lower. We can rationalize this behavior if we actually look at the plasma energy of the system. And here I'm talking about the plasma energy, the plasma that is formed by these added carriers in the conduction band bottom, okay? So this is the plasma energy. And you see that this kind of transition between a polaronic regime where you have a large-ish mass renormalization to a regime where the electronic quasiparticles are weakly interacting. This transition happens when the plasma energy becomes larger than the characteristic phonon, longitudinal optical phonon energy of the system. What this is telling us is that basically when the plasma energy is large enough, or correspondingly when the density of electrons is large enough, then the polar coupling is suppressed. So this is very interesting, and it suggests a way to engineer the electron-phonon coupling when the longitudinal optical electron-phonon coupling is the dominant one. Now, if there are no questions in the meanwhile, I will move to not the second part.
I did have a quick question about your last slide. And also actually maybe just going back a little bit earlier just to make sure I'm understanding. So the Migdal one-shot calculations you did were just based on that matrix element, and then also did you just take the electron dispersion to be quadratic, or?
No, it's an ab initio band structure from density functional theory. So okay, there's no model.
So the density functional theory gave you effectively the band structure, and you put that into the Migdal.
Yes, this band structure here.
Okay. Yeah.
Can you see my mouse, by the way?
Yeah.
Okay, perfect. I wasn't sure.
Yeah.
So why don't you interrupt? Okay, go ahead, Sarge.
No, so I was just going to ask you about the Fermi liquid crossover thing. How is that calculated? What is done there? I'm not sure I followed the calculation.
Sorry, could you repeat
the very last slide you showed us? I wasn't quite sure how you obtained that.
So the mass normalization is actually calculated from either from really the derivative of the real part of the self-energy at the Fermi level, or you can actually do a parabolic fit of the bottom of the conduction band, or you can do a parabolic fit, or you can do a linear fit near the Fermi level. This will give you the mass normalization, and the two estimations are absolutely equivalent. The plasma energy instead is estimated from the electron gas model, but you can actually also calculate that directly from first principles if you want, and we did verify that. So it's just quite lengthy to calculate. So you can calculate the electron energy loss function. So you take your crystal, you insert some extra electrons, and you do the calculation basically of the dielectric function, and you look at which energies are the peaks of the electron energy loss function, and that the low energy peak will correspond to the plasma energy that I'm talking about.
Okay, great, thank you.
Yeah, I also had actually a little bit of a question. So the way that the extra electrons come in your model, is that only through this dielectric function that you add that screens the electron?
And also through a shift of the Fermi level into the conduction band.
I see, right. But do you, and another question is, do you mentioned several times that you do this at the DFT level, or do you do this at the do you treat the electrons?
Okay, so no, we don't do GW. We could. But we don't. One of the reasons is that there are calculations, for example, on the band structure of TiO2, where it's kind of shown that GW is mainly a rigid shift of the bands. So there are materials where GW can also change a lot the effective mass from DFT and so on. But first of all, it's not what we wanted to focus on, and second, we kind of saw that doing GW would have been mainly like a rigid shift in this case.
Okay, thank you.
No problem. So I will try and spend a little time on this second application, because then I'm eager to talk about the second part of our studies. So the second application is europium oxide. And as I told you, in this case, we were approached by experimentalists who did ARPES on this material. So first of all, let me just show you the band structure of europium oxide. So it's a ferromagnetic semiconductor, which can also be doped. Basically you would insert, you would have some electrons here at the bottom of the conduction band at the X point. This is our DFT band structure. And this is, for example, the ARPES intensity map for this region here. Of course, it's kind of blurred, but you see it sees the same features that we see in our ab initio band structure. And then if you zoom here at the bottom of the conduction band, where it looks like there's nothing, there is actually some signal. And you see there is the main band at the bottom. And then there are these satellite replica underneath again. So since they knew that we did this sort of calculations for TiO2, they asked us to do the same for europium oxide. And indeed, we observed this satellite replica when we calculated the spectral functions, including a self-energy that had the interaction with longitudinal optical phonon. By the way, I probably never used the name Fröhlich before, but this sort of interaction with longitudinal optical phonons, which is a long-range interaction, it's often named the Fröhlich interaction, since Fröhlich is the one who first wrote the Hamiltonian for that. So this is quite satisfactory. You see that actually the intensities that we get for our spectral function profile are not exactly matching the experiment. This could be due to various effects, but of course, we didn't actually look further into this. What we looked more into is this. So in the experiment, you could actually see that when you increased the doping level, the satellite would actually blue shift relative to the quasi-particle peak. So you see this is low doping, and then you increase the doping and the satellite moves a little bit further and further, and then at some point you don't even resolve it anymore. Now this is not compatible to interaction with our phonons, because the phonon frequencies changes very little with the doping, and actually it could only decrease, not increase with doping. So what this hints at is the fact that now our electrons are coupling to the carrier plasmons. So I'm just going quickly back to the slide before where I showed you the self-energy, because I wanted to tell you that this self-energy can be generalized to describe the interaction of electrons with bosons in general. And we showed that in particular, if you take this energy as the plasma energy, then the matrix element has this form here. And I'm not going into too much detail, but it's basically analogous to our Fröhlich Polaron. So if we do calculations where we include both the electron-phonon self-energy and the electron-plasmon self-energy, then we get this sort of spectral function. So at low doping, it's basically what I showed you before. And then at increasing doping, you see that we also get a satellite that has a larger energy separation with respect to the main peak. And actually at larger doping, it becomes actually very dim. And then we just have a kind of broad tail and no clear satellite anymore. From the experiment, you can actually extract the so-called phonon loss and plasmon loss. So this is simply the energy separation between the satellite and the main peak. So you see that indeed, as I was telling you before, there is one peak that can be resolved that is due to the interaction with phonons, which is roughly at a constant energy. And then the interaction with plasmons instead gives you satellites with energies that increases with the doping, and it's actually compatible with this parabolic dispersion of the plasma energy. from the experiment, it's not really possible to extract the mass renormalization parameters because there is not enough resolution, but we did it from the theory. And you can see this is the total electron-boson coupling strength. And this is the one due to the electron-phonon coupling alone, and this is due to the electron-plasmon coupling alone. So you see there is the same behavior as before. The electron-phonon coupling decreases. And in fact, after this density level, you don't discern this, you don't see the phonon loss peak anymore. So this is very interesting. Basically, it shows that in this material, you can really talk about phonon and plasmon polaron, and the coupling strength is even more tunable with doping. We actually wanted to do something more. They asked us to try and estimate what would be the plasmonic polaron structure. So we tried to do this using many-body perturbation theory, and we actually kind of failed. So what happens is that if you use perturbation theory, you will never achieve self-localization. You will get a Polaron wave function that gives you an increased probability of finding the electron near the center, but then you will always have a probability, still a finite probability of finding the electron at infinite distance from the center. So the only thing that we achieved to do was to use a model. This is the Feynman model. The Feynman model is actually the most exact solution of the Polaron problem, but it's the ideal Polaron problem. So it solves the Hamiltonian where you have simply a single electron interacting with a single boson. And this is the plasmonic Polaron radius. It depends inversely, inversely on the so-called alpha parameter, which is related to the electron-boson coupling strength. And it also depends on the boson frequency. So here, the plasmon frequency. So here in red, it's the estimation of alpha, which is the coupling strength with respect to doping. So you see it decreases as expected. But also the Polaron radius decreases with the doping. And this is kind of counterintuitive because for a standard phonon Polaron, you would expect that when the coupling decreases, the Polaron radius becomes larger. Instead here, the Polaron radius becomes smaller, and that is due to the strong density dependence of the plasma energy. So this is nice, but we weren't fully satisfied with it because, as I said, we had to use a model, and with our perturbation theory tools, we could not really describe the electron localization. So what we did was really to go back to the origins, let's say, to try and describe our polarons a bit better. So I'm just going back to the image that I showed you at the beginning. So this image that shows you how the electrons is basically distorting the crystal field and inducing a displacement of the atoms, and the electron itself can localize. Now, this idea was actually first introduced by Pekar and also Landau in the 40s and 50s. And then so many people worked on the Polaron problem from an analytic point of view. Now, I want to just briefly recall this Landau-Pekar model because this is really, it really includes the essential physics. And it was our starting point to write a theory that was describing the same physics, but from first principles. Now, this model deals with a single electron added to a polar insulator. And so this electron travels in the crystal, and because of these electrostatic interactions, it might get self-trapped. So it is a continuum model, meaning that the Polaron is assumed to be extended and to be large enough that the atomistic details don't matter. Then it is actually quite easy to derive this, this expression. This is the total energy of the Landau-Pekar Polaron as a function of the Polaron wave function psi. So you see there is a kinetic term. Here the prefactor includes an effective mass that effectively deals with the interaction of this extra electron with the electrons in the crystal. And then this is the electrostatic part. And you see it is crucial here that there are these two constants. One is epsilon infinity, and this is the so-called high frequency dielectric constant. So it includes the screening only due to electrons. And this is the so-called static dielectric constant, which is kind of like a misleading name. But basically it includes the dielectric screening of both the ions and the electrons. Now you can see that if material is non-polar, then these two epsilons are the same. And so this term vanishes. But in a polar insulator, this is non-zero. And once we have this total energy functional, basically, we can write a Schrodinger equation by minimizing this with respect to our wave function and introducing a Lagrange multiplier, this epsilon here. So this can be solved numerically almost exactly. But for our purposes, even a simple trial wave function serves quite well. Actually, if you take a trial wave function that has this exponential decaying behavior, you get to an energy expression that is almost the same as what you get for the exact solution. So we have this expression. This is the energy of the Landau-Pecard polaron as a function of the polaron radius. So you have the kinetic term and the electrostatic term, and the sum of these two terms is negative. There will be a radius that minimizes the energy, and so that will be our actual self-trapped Polaron energy. So from this minimization, we can get the Polaron radius and we can get the Polaron energy. And here I wrote it explicitly in terms of this alpha parameter that you saw before as well, because you find this alpha everywhere in the Polaron literature. Of course, this alpha contains this numerical parameters, 1 over epsilon infinity minus 1 over epsilon 0 and so on. So this is the essential physics, but this is a model that, as I said before, assumes a single band, no actual phonons. The crystal is treated as a continuum, and it can only treat the type of polarons that are called the Fröhlich polarons. So the ones that comes from the interaction with longitudinal optical phonons, essentially. But there can be also, for example, piezoelectric polarons, acoustic polarons, and so on. So what can we do from an ab initio point of view? Well, we started from the actually just the total energy functional of density functional theory. And actually, this gives me the chance to introduce DFT for those of you who are not first principles experts. So in DFT, if I want to describe the energy of a crystal, so now we're talking about a semiconductor or an insulator, an ideal one, so all the valence bands are filled, then the total energy is given as a functional of the density. This is the Consham formulation, so psi V are the Consham wave functions, the valence wave functions. So we have the kinetic term. This is the Hartree term. This is the exchange correlation energy. This is the interaction with the ions, and this is the interaction between the ions. So what people do in DFT if they want to calculate polarons is that they actually take a supercell, they add an electron, or they take one out if they want to study a whole polaron. But let's say they add one electron, and then they can relax their supercell configuration and see if they achieve a solution where the ions are a bit displaced and the electron wave function is localized. This is done a lot in the literature, but it's got some serious problems. One of the problems is the fact that the Polaron self-localization and the energetics and so on strongly depend on this exchange correlation functional. And the reason for this is mainly the so-called self-interaction. So when you add one electron in DFT, you're actually also including the interaction of the electron with itself, which is of course unphysical, is one of the known problems of density functional theory. And there are various solutions for this, but this poses a serious problem for Polaron calculations in DFT. So what we wanted to do was to really find a rigorous formulation that didn't have this drawback. So we wrote the total energy of an added electron. So we do the same thing as what you would do in an actual DFT calculation. So you add an electron and you write on paper what would be the total energy. But then what we do is to make a couple of assumptions. One is the fact that we say that when we add one electron, the valence electrons are not perturbed. This is an approximation, of course, that needs to be verified, but it's a reasonable one because we're looking at the, one single electron added in the whole crystal that is ideally infinite. The other approximation that we do is that we expand the total energy in terms of the atomic displacement. So as you know, once you add an electron, the atoms can displace. And so we assume that the displacements are small enough that we can expand the total energy, and we stop at the lowest order that admits a non-trivial solution. So this is it. This is the total energy of the ideal electron. This is with respect to the total energy of the ideal crystal. So it's not written here, this term. And you see it includes the Consham energy. This is the Consham Hamiltonian of the ideal crystal. And this is the derivative of the Consham potential with respect to phonon displacement. Delta tau is the phonon displacement. And of course, psi is the wave function of the added electron. And then this extra term here has the C is the usual matrix of interatomic force constant. So this is basically the elastic energy of the lattice. Now, what we have to do now is to do the usual thing that you do in DFT. You minimize this functional, but this is a functional of both the extra electron and of the atomic displacement. So we minimize this functional with respect to both. And we introduce the usual Lagrange multiplier that takes into account the normalization of the electron wave function. So when we do that, we have these coupled equations. And these are actually, if we plug this delta tau inside the first equation, we have this expression here that looks awful, but believe me, it's not that awful. And it basically is the ab initio version of the Landau-Pecquer Polaron equation. This time we have much more physics in it though, because this time we are treating the lattice as not as a continuum. We have an actual band structure. And we are taking into account all possible electron-phonon interaction. So you see the Consham Hamiltonian plays the role of the kinetic term, the one-body term with the effective mass that was in the Pecquer equation. And then this uglier term is the electrostatic part. Now we could solve this, but it's not what we want to do because this is again, it's done in a supercell. Now the problem is that when you add an electron in a supercell, the self-localization can also depend a lot on the size of the supercell that you're considering. To say it even more easily, imagine that you have a large polaron that is localized over quite a few lattice parameters. Well, then you would need a very large supercell to describe this object, and this is simply unfeasible from ab initio. But there is something clever that you can do. You can go in reciprocal space. I will just try and be as concise but as clear as possible. So in DFT, you have these objects here, the Consham wave functions, and these form a complete basis. So you can take the Polaron wave function psi in real space and expand it as a linear combination of Consham wave functions in terms of these coefficients A. And you can do the same for the atomic displacements. You can expand them in terms of this E. These are the phonon wave vectors, okay? And this is done in terms of the coefficients are called B. If you do this, and you do quite a bit of algebra, which of course I'm gonna spare you, you get to these two equations, which is basically a self-consistent eigenvalue problem. And this can be solved, and you can obtain A and B self-consistently. And once you plug A and B into these expressions here, you have your Polaron wave function and you have your atomic displacements. And I really want to stress that this can be done by simply using ingredients that come from standard DFT calculations in a unit cell. So you don't need supercells anymore. you see these summations over K and Q. These K and Q are reciprocal space wave vectors. And so the reciprocal space wave vectors will basically mimic the supercell. So if I do a summation over a grid of 10 by 10 by 10 wave vectors, this is equivalent to a 10 by 10 by 10 supercell, just as an example. So let me show you some results to convince you about what we're doing, really. So first of all, we can calculate the energetics of the Polaron. So the energetics of the Polaron is given basically by this Polaron eigenvalue here, epsilon. But this is not actually the total energy of the Polaron. The total energy of the Polaron should also include a contribution of lattice strain. This is normally defined also in normal DFT calculations as the minimum of the total energy where you have the added electron and the atoms are displaced, minus the minimum of the energy when you have the added electrons, but the atoms are not displaced, okay? This is basically described by this configuration diagram here that you can see in many, many papers. So this Polaron formation energy is basically the energy that it takes to, you take an electron in a localized state, this orange line here, you promote it into a delocalized state, let's say the conduction band bottom. This vertical energy would be this Polaron eigenvalue, but then the system would relax to another minimum where the atoms go back to their undistorted position. And then this energy difference would be the Polaron formation energy or the Polaron total energy, however you want to call it. So these are our results. You can see that actually these are energies versus the inverse supercell size. As I said before, the supercell size for us is the number of K points in our reciprocal space grids. But it doesn't matter because there's a one-on-one correspondence. So you see that for the case of an electron polaron in lithium fluoride, you would need supercells larger than 11 by 11 by 11, which is like 3,500 atoms, in order to achieve self-localization for your polaron. Now, this number is, believe me, unfeasible in DFT. But actually, if you really wanted to converge your description of the polaron, you would need to go to much larger supercells, which is even more unfeasible. This is because the electron polaron in lithium fluoride is a large polaron. This linear behavior of the energies with respect to the inverse supercell size has to be expected. It's similar to what happens in a charged defect calculation in a supercell. There is a spurious interaction between defects in the supercell's replica. And so you actually need to extrapolate to infinite supercell size, which you can easily do because you do calculations at varying size and then you can linearly extrapolate. Another thing to notice is that you see this shaded region here with MIT written. MIT stands for metal insulator transition. What we want to say here is that if you imagine to have more than one added electron, okay, so if you have a large enough density of added electrons, then these will not they will not localize, but they will form delocalized states due to the interaction between each other. So this is why when you have a smaller supercell, you don't have self-localization. But in the dilute limit, you do, and this is the energetics. By calculating, by solving our Polaron equations, we can actually have a realistic view of the electron wave function. We can say what is the shape. This is mainly like an S state. The radius is about 10 angstrom. Here in this plot, you can see the atomic displacements. Okay, so in green, the lithium, and in blue, the fluorine atoms. So you see how the atoms displace over what range. And you see that, for example, the fluorine atoms are the ones that displace the most due to the presence of this added electron. We can actually do more with our theory. Remember, what we did was expanding the Polaron state in terms of Consham state and the phonon displacement, the atomic displacement, sorry, in terms of phonon eigenvalues, so eigenvectors. So if we plot the expansion coefficients on top of the electron and phonon band structures, this is what we get. What we get is basically a quantifications of what are the electronic and the phononic states that really contribute to this polaron. So what this tells us is that the large electron polaron in lithium fluoride is mainly composed of states here near the conduction band bottom, and the phonons that take part in it are mainly the long-range longitudinal optical phonons. And this is what you would expect for simple models of lithium fluoride, where you would expect that this is the physics, this is what's going on. But actually, it's not just that, because there is also sizable interaction with acoustic phonons, which you would not expect, and you would not be able to quantify if you used a simple model. This is instead the case of the whole polaron in lithium fluoride. So the theory is perfectly symmetric for holes or electrons. So we can do calculations for whole polarons. These are the formation energies. And this is the eigenvalue. So the eigenvalue is positive because it's measured with respect to the valence band top. So you see that this is now a small polaron. We can achieve localization already with a 2x2x2 supercell. Sorry, this is a projection of the charge density on a plane, and these are the atomic displacements as before. Now you can see that the electronic states that are involved in this polaron are all states here at the top of the valence band, and the phonons that interact with this with the electron are mainly, again, the longitudinal optical phonon, and mainly at short wavelengths, sorry, large wavelengths. So this is what in the literature people would call a Holstein polaron. So it's not simply the parabolic band, but it's a flat band interacting with long-range optical phonons. Again, this is not, we didn't discover this because we made an a priori model. We discovered this by doing fully first principles calculations. This is my very last slide. I just wanted to tell you one more thing without any details. So I told you before that density functional theory has a serious problem that is due to the self-interaction correction. Sorry, the self-interaction contribution to the total energy. So if we take another material, which is in this case lithium peroxide, and we do an explicit density functional theory calculation in a supercell, we obtain a wave function for the polaron that is not really localized. It is kind of localized because the polaron here is small enough that even standard DFT gives you a localized solution, but only localized over one direction and not the other one. If we do the calculation using our method, we get this nice localized polaron. We proposed a way to eliminate the self-interaction in DFT for the polaron. And if we do that, we obtain this very, very similar wave function. And this is also validation of our method, of course. Now I really should conclude. This is a brief summary. So it was really kind of two parts of, my talk was kind of two parts. In one part, we looked at how to describe ARPES spectra of doped oxide from first principles using many body perturbation theory. And this allows us to describe the phonon and plasmon polarons in these materials. And this approach has advantages and drawbacks. One drawback is that, as we said, we weren't really able to describe Polaron self-trapping. And so I introduced to you a new theory to describe polarons via, let's say, a density functional perturbation theory approach, which doesn't use supercells and really allows us to get the wave function and energies of both large and small polarons. Before finishing, I should thank again all the people that did work with me, in particular Feliciano Giustino, of course, and Wenhong Xiu, who is actually the main author of the Polaron density functional perturbation theory approach. And thank you very much for listening. And I'm really happy to take questions.
Okay, thank you very much. So So if you have questions, you know, either just unmute yourself and ask your question, or if you want to pose a question in the chat, you can also do that.
So I guess I had a question. It was, so you showed us, in fact, in the second last slide, you showed us that picture of that S-wave function. Yeah, the one after this one.
Oh, sorry.
Yeah. So this is what you got from your very nice first principles calculation. But it also looks a lot like what you might have got from the Feynman calculation, right? It's just S-wave, and it's...
that is correct. That is correct. And this is because it's a large polaron that is very much like an ideal Fröhlich polaron.
Mm-hmm. So in principle, it could have turned out that it was more affected by the presence of the lattice, and you would have seen that, and Feynman would not have. And I guess that's the gain. That's what we gain by doing this.
What we gain by doing this is that we don't make any assumption on the type of polaron that we have. And, you know, we can have a polaron like this, or we can have a polaron like this, or we can have a polaron like this, and we make no assumptions. We can describe either type using the same theory. And we gain much more insight because, for example, if we had used the standard Polaron model, we wouldn't have gotten an interaction with acoustic modes, and the energetics would have been a bit off, and so on.
Right. Okay, very good. I think I understand. Thank you.
Thanks.
Very nice job.
Maybe I'll ask a question while we see if other people come up with questions. But when you add this extra electron, how do you deal with the electrostatics? Do you have to put in like a compensating background like we do
in the theory, in the derivation, you will see that we did put a compensating background, yes.
So where did that?
But then in our actual calculations, we don't explicitly put an extra electron in a supercell. We actually solve these equations, which simply include ingredients that come from density functional perturbation theory without explicitly adding any extra electron. But then, for example, we have this spurious Polaron interaction that gives this linear dependency of the energy. And so you need to extrapolate. But in practice, when we solve our Polaron equation, we never add explicitly an electron, so we don't need to deal with electrostatics.
I see. Okay, right. So that's taken care of by this second term that you do. Okay. So when you have while we're on this slide, you have this sum over all A and K there. That includes both occupied and empty states, right? But
no, actually, thanks for pointing that out. This sum over n is only over unoccupied states or occupied if we're describing a hole. And this is because, as I said, we're making the assumption that the valence states are not affected by adding this electron in the supercell. And so this means that our Polaron state needs to be orthogonal to the valence states. So this summation can only include conduction band states. You could argue, okay, how do you know that this is a good enough approximation? Well, this is why we validated the theory a posteriori. We validated this both on the small Polaron in the case of lithium fluoride, but we also validated it using the basically the standard Fröhlich Polaron model for the large Polaron case.
So if you're doing a whole Polaron, then it's a sum over only over the occupied state.
Exactly. Yeah.
In your other picture, it shows that it's actually usually only like one band that comes in.
So then it turns out that, for example, what is it? So it turns out that yes, there's basically one band only that contributes. Also here. But I didn't show these plots for lithium peroxide, but in lithium peroxide, you can see that there's two bands that contribute in the same way. So that's actually an interesting thing to observe.
Okay. So are there any other questions in the meantime?
I have one question. Hi, Carla. Thanks for the nice talk. So you discussed the European oxide. That doped the European oxide?
Yes,
right?
you want.
Yeah, so I know that European oxide on a certain temperature, it's ferromagnetic. And
yes.
There used to be many discussions on, how to modulate the Curie temperature by doping, like oxygen deficiency, things like that. And it has been a controversial. Just wonder if we have gained, like there are several mechanisms, including bound magnetic Polarons, things like that. I just wonder, if recent theoretical investigation has gained new insight into this.
So we discussed it briefly with Phil King, who did the experiments and so on. But we didn't do any calculations. But what the experimentalists observed was that these polaronic features disappear very quickly with increasing temperature, actually well before hitting the Curie temperature. So in practice, we did not try and explore this further, and I can't really speculate much of what the implications are for modulating the ferromagnetic temperature.
Okay, thanks.
So while we have this picture up, were you telling us here that these plasmon-related peaks, were they related to like the higher conduction band, which has the opposite spin, or?
In practice, a spin doesn't really play a major role. Like, we need to take into account that the bands are spin polarized, but that's it. So it's, I mean, the fact that it's a spin polarized electron gas doesn't have any major physical implication, but apart from obviously changing the occupancy of the bands and so on, because the spin splitting is large enough that it doesn't really play a role.
Yeah, I see now. I missed the scaling. Okay, yeah.
Mm-hmm.
But the question brings up another interesting point, maybe, that there exists also this notion of a magnetic polaron, which I think is some kind of interaction of an electron with, you know, magnons or something, which are yet another set of bosons, which, so it's another potential future application maybe of the method.
Yeah, that is even harder to study. I mean, in fact, like electron-magnon coupling, I'm aware of, you know, there's something in the literature, but it's very much quite unexplored still. I think there's more on that at the level of models, but at the level of first principle calculations, not yet. And I think it's even harder to measure experimentally. And to kind of pinpoint that this is magnum polaron and so on.
Okay. Well, there's quite a lot of work in connection with the cuprates on that kind of thing, where you have you know, spin waves and holes. Polarons here. I mean,
I'm just saying that at the level of first principles, we're still behind.
Yeah, but it'd be great if you could catch up, because experiments and very little understanding.
Yeah, no, actually, I mean, theoreticians always have a hard time catching up with experimentalists.
Yeah.
Okay. Well, actually, there's also been work in connection on these magnetic polarons with, in the context of dilute magnetic semiconductors in manganese doped gallium arsenide and so on, you know. But given the time, if there are no further questions, then maybe we should thank our speaker again, and you know, so thank you.
Thank you.
I know the applause is always
no problem.
Okay. All right. So
well, thank you for listening.
Sure. So we can start the recording now.
Yeah.